Good day. My name is Yannick-Leon Kardeis. I'm from the Rheinland-Pfälzische Technische Universität Kaiserslautern-Landau, and I warmly welcome you to my presentation here at the Information Physics Institute. Today I will show you the key findings from the paper, The Universal Fractal Chirality of Riemann Zeta Function. Here you can see the table of contents for today's presentation. We will begin with the fractal structure that we discovered. After this, we will compare it to Julian sets and the Mandelbrot sets of the zeta function. Following that, I will present another fractal pattern that correlates with prime number spirals. And next, we will explore connection to quasicrystals, followed by an analysis of mirror symmetry. Then I will show a comparison between a Smith chart, the fractal structure, and an electromagnetic dipole field. In the seventh section, I will demonstrate how geometry links chemistry, physics, and mathematics. Finally, the last two sections will address the question, why do these fractal patterns keep popping up in nature? And the last point is fractals, the zeta function, and the nature of information. So we identified a fractal within the Mandelbrot set that shows a geometric similarity to the analytic continuation of the Riemann Zeta function. Both of them are defined in the complex plane, which allows a direct comparison and also suggests a link between number theory and fractal structures. Here you can see in the upper part, the analytic continuation of Riemann Zeta function, which is defined in complex plane. And we found a fractal, which looks like an electromagnetic dipole field that shows the same pattern like Riemann Zeta function. We see here the circles, the symmetry, here the poles, and the red line marks precisely where the non-trivial zeros are expected to lie. And in comparison to this fractal, we see this fractal has, at this point, a strip which suggests a link. And yeah, the only difference is that the analytic continuation is mathematically smooth, while the fractal structures appear rough and self-similar. Next is the comparison with Julian and Mandelbrot sets of the zeta function. We compared our fractal to Julian and Mandelbrot sets related to the zeta function based on the work by S.C. Woon. These sets are made by repeating functions from zeta function and look very similar to the fractal we found. Yes, in this picture, we see the fractals made by Woon, and we see the similarity like this black pole here, this here, and also the symmetry, which is also beneath the first comparison, a good evidence of that the zeta function is a fractal. And yeah, so then we go on. Next is prime spirals and zeta function fractals meet Dirichlet. We found a fractal pattern that matches how prime numbers spread out when they plotted in polar coordinates. And these spirals connect to Dirichlet theorem about prime numbers. And the fractal shows up when you zoom into the analytic continuation of the zeta function. That means if you keep zooming in the first fractal I showed, then the next structure I will show you appears. So this is the structure we found in the upper left. And in this picture, we see these prime spirals plotted in polar coordinates, which is also in complex plane. That means these two are in the same area. And for example, this red stripes could be seen here and here. We see also this wave-like behavior. And for example, when you go at this point, these black points, black oval points, and when you look at the prime spirals, you see in this area also locations where no prime numbers are plotted, and it repeats. And then I also analyzed these pictures for a long time, and almost every black point can be seen also in this spiral pattern. These two pictures are the same picture like this, but you came to these two pictures when you zoom in this area. So that means this picture is the same as this one. So fractals and quasicrystal scattering patterns, very interesting. We identified a fractal structure that matches the periodicity and scattering behavior of quasicrystals. This agrees with the predictions made by Torquato and his colleagues from University of Princeton. They made 2018 experiments with X-rays and quasicrystals, and then they compared it to prime numbers, and somehow the fractal we found shows exactly the same structure like the predictions they made. So in this picture, in the upper section, we see the diffraction by prime numbers and the periodicity. And if you look at these points and apply it to this fractal we found, then you see the same periodicity, like here, a big one, a small one, then a big one, and between them, many very small points. Also, you see the fractal pattern they predicted, and you can also go in this section and say like, okay, we take this scattering angle and go from this, and then we know it follows by a smaller one, then a medium one, and you see this pattern here is the same, and also the periodicity. We also compared the fractal structure to a quasicrystal, and the similarities are marked with colored arrows. Yeah, we see here the center in the middle, then these structures, for example, here the yellow arrow, the smaller one, and the position of the bigger ones. So the only difference is when you count these points, which are analytic continuations, then you have less than a normal quasicrystal. But except that, everything is the same. which is very interesting. Next, we mirrored the normal distribution of prime numbers to show its similarity to the fractal. And this creates a structure like the fractal resembles a dipole field. This also shows that prime numbers must be mirrored exactly at the point 0.5 by the analytic continuation. So in this picture we see we just mirrored the normal distribution of prime numbers and then received something which looks like this electromagnetic dipole field. And we also have these two strips marked with red arrows. Then here these poles. And you see beneath this, this black point between. So the next point, zeta fractals and field echoes of electromagnetic structure. We compared visualizations of the Smith chart, which is also used in electrical engineering, the fractal we found, the analytic continuation, and dipole field. And we identified a striking geometric similarity between all those four structures and found, for example, like symmetries, rotations, and field-like patterns. And these similarities suggest a deeper correlation with electromagnetic wave behavior. So in this picture, we can see this comparison we also had previous. And this is a Smith chart used in electrical engineering, which shows the same geometry as the zeta function. But in this point, this is linear. And in this point, we are in complex plane. So this means you have to imagine this here when you plot it into complex plane, then we have the same geometry and also the electromagnetic dipole field, where you can see the similarity to the fractal we found. So we got a link between all those four, and we can now explain, for example, the connections between prime numbers and electromagnetic aspects they have previously found and hasn't been and they don't understand until now, maybe. And yes. So the next point, linking chemistry, physics, and mathematics through geometry. We demonstrated a connection between chemistry, physics, and mathematics via geometry. And we compared the discovered fractal of the analytic continuation with quasicrystal structures, showed how geometric principles explain the emergence of these interdisciplinary connections. And yeah, so again, I'm going to explain. So this is the fractal we found. We also showed the connection to analytic continuation based on geometry. And if you keep zooming in this area, then this structure appears. That means we have a direct link between chemistry, physical chemistry, and mathematical structures based on geometry, and prime numbers has connections in all these sections, but we never knew why these connections, or where these connections come from. And this is my way to explain how they are interconnected. Yeah, so we see a direct link between three disciplines, and yes. So, point 8. Why do these fractal patterns keep popping up in nature? Is very interesting because iterative growth leads to fractal shapes, which means natural systems prefer this because they have minimal effort and maximum output. And this is how nature, for example, they always is looking for easy ways to solve complex problems with simple aspects. So the last slide we have is Fractals Zeta function and the nature of information. For example, if the Riemann Zeta function contains fractal structures, then this complexity pre-existed its human discovery. That means the Zeta function maybe existed even before Riemann could have think about it. And these fractal and the information was there before computing. So that means only we can't see these only because we can't see these fractal structures before we compute it doesn't mean that the information doesn't exist. And this raises deep questions. For example, is mathematical truth discovered or created, or does information exist independently of observers? Yes. So here are the references. You can also find every reference within the paper. And yeah, if anyone has some questions, then I'm going to try to answer this. But I also have to say that it is very hard to explain this topic in English, but yeah, I'm going to try it. Thank you.